Okay, hello guys. Nice to see you. Some technical issue. Hello. Yeah. I don't know. It's not so sunny here. It was sunny in the morning, but already quite foggy and on campus. Hi. Sure, sunny inside is very important. That should be always climate under control inside, at least as much as possible. Okay, I believe that most people have joined. So last discussion we spent introducing the concept of center of mass and did some calculations. If I'm not mistaken, we did calculation for the center of mass for a uniform rod. So I promised you to proceed further with non-uniform rod when we have some linear distribution of density along the rod. So this factor should be taken into account because for previous example, we got center of mass right in the middle of the rod, which kind of expected result. It just shows that our calculations were correct. Now we need to apply the same general approach, assuming that this lambda linear density is not uniformly distributed. So it depends on x, and that dependence will be taken into account into our calculations. Okay, so let me change the screen. And this time we assume that lambda is equal to alpha times x. And we recall the equation for the center of mass equal to integral x times dm. A general equation. So now we substitute instead of dm, its expression taking into account this linear distribution of the density lambda. So we can write that x cm is equal to integral x. Previously, we were writing just lambda times dx. However, it's not a constant anymore, so it goes alpha x times dx. And this will be from 0 to L, integration along the whole length of the stick. So this will be alpha is a constant. We can take it out from the integral from 0 to L. Here will be x squared dx. And sorry, actually I forgot something important. Here should be 1 over m, which is the total mass. So here will be 1 over m and alpha divided by m. So alpha divided by m x cube divided by 3 from 0 to L. So when we substitute these limits, we will get alpha times L cube divided by 3m. And as you remember from last time, we need to substitute here also expression for this total mass. Any ideas how we define this total mass? Suggestions?
Like we have density.
Okay, can you clarify it a bit more clear? So mass is equal to what?
Volume over density.
Length.
Linear density times length, yes?
Yes.
Okay, so this was true for the previous case when we had lambda constant. So this is correct equation. However, it doesn't work for the case when lambda is not constant. So in order to get total mass now, we need to actually do this integration. So it will be total mass will be equal from 0 to L times d m, some small element of this mass, which will be from 0 to L. Okay, here should not be this limits because we need to go from dm to dx. And that we do as alpha times x, which is our lambda, times dx. So now we can integrate from 0 to L. And alpha is a constant. Then we have integral of x dx from 0 to L. So here we have alpha times x squared over 2 from 0 to L. And this is equal to alpha L squared divided by 2. So now we have equation for total mass, which takes into account this linear distribution. Lambda is equal alpha x, and we can substitute it here in this equation. So for x center mass, we will get alpha times L cube divided by 3 alpha L in second power, and here will be this 2 from the denominator. So we can cancel out this and this, this and this. And we eventually get that it will be 2/3 of L. So you see that's already not 1/2 of L, not in the middle, but already shifted towards the further end. So if we have our rod, this is the total length, L, and this is the origin of coordinate X. So here somewhere will be 2/3 will be X center of mass. And that's why the reason why it's shifted from the middle towards the like further to the right, because then linear density increases like this. So it's heavier in this right part of the stick. And center of mass is shifted towards there. Okay, so with this, we kind of discussed these moments. So definitely should remember for total mass, if you don't have uniform distribution of density, then you need to do additional integration to calculate the total mass. Otherwise, you cannot apply this simple product of density and length. Good, let us proceed further what this center of mass is useful, actually. So let us consider some system of many bodies. And in general, as we defined during previous discussion, the position vector of the center of mass can be determined by the following equation. So 1 over total mass of the system, sum from, like, for all bodies which form the system from 1 to n. Then position vector of each body times its mass. So now we can, since we have position vector, we can go one step further and get velocity vector. Velocity vector of the center of mass is nothing else as first derivative of the position vector over time. And now we can write that it will be equal to 1 over m sum from I equal to 1 n mi times dr I over dt. This will be velocity vector of each body, and we can eventually write 1 over total mass sum over, like, from I equal 1 to n mi times vi. So this is how we get the velocity vector of the center of mass. And now we have this total mass. So if we put it in the left side of the equation, we will get total mass times velocity vector of the center of mass will be equal to the sum over all bodies mi times vi vector. And that is sum of all linear momentum vectors. And we can write it that it's total linear momentum vector of the system. So this product of the total mass and velocity vector of the center of mass gives us total linear momentum of whole system, which is quite convenient. Means instead of calculating for, I don't know, unlimited number of bodies and sum them up, if we know the center of mass and total mass of the system, we get the product gives us total linear momentum vector. That is very useful. And next step, obviously, we can proceed to acceleration of vector of the center of mass. So acceleration vector of the center of mass is equal to the derivative, first derivative of the velocity vector over time. So this is 1 over total mass sum all over all bodies in the system mi I times dvi vector dt. And this is 1 over total mass I like over all bodies mi times ai vector. Again, we transfer this total mass to the left side of the equation. We get product of total mass to the acceleration vector of the center of mass, and that gives us the sum of all these products mi ai for each body, and that is nothing else according to the second law of motion as the sum of all forces which act on all bodies in the system. So this product will define all forces which act on the system. What is important here, we need to mention the third law of motion, and there we remember that it's like F12 is equal to minus F21. That means, so by pairs, all internal forces between the bodies will be canceled out because they are equal in magnitude but opposite in directions. So that's why we can write, taking into account this third law of motion, we can write that the product of total mass of the system to the acceleration vector of the center of mass will be equal to the sum of all external forces which act on this system of many bodies. So that is also convenient because, let's say, we know external forces, and then we can predict how this system as a whole will move with which acceleration vector based on the total mass of the system when we operate with the center of mass concept. So now let us do the following. For this last equation, let us integrate this. So if we integrate it, so let's put force in the left side of the equation, sum of all external forces, and that is actually like over dt. We integrate it over some time interval. So we remember that f times delta t, it is some, this is vector, is some vector which is called impulse of the force. So that is impulse of the force, like of the resultant external force which acts on the system of many bodies. That will be equal to integral total mass times acceleration of the center of mass dt. We can represent acceleration as dv over dt, like first derivative of the velocity vector. So let us do it. dv center of mass over dt times dt. So here we already can cancel this dt, and we end up with total mass, which is constant, doesn't change, so we can take it out from the integral, dv center of mass. And eventually we will get total mass times delta v center of mass. So this is delta p total. So we see that impulse of the resultant external force of the system of many bodies will be equal to the total change of the linear momentum vector of this body or system of many bodies. And if the sum of all external forces is equal to 0, so we have either isolated or quasi-isolated system. So when, for instance, all external forces compensate each other, then we can write that m times acceleration of the center of mass is equal to, let's define also as a derivative of velocity vector, dv center of mass over dt is equal to 0. So because here, like this impulse of the external force will be equal to 0, since external force is equal to 0. So that means that the product m v center mass vector is equal, we know it's equal to total linear momentum vector and remains constant. So if we have isolated system, this equation, like set of equations, tells us that linear momentum vector remains constant. So we have conservation of linear momentum vector for such a system, like of many body system, also in terms, so it's given in terms of velocity of the center of mass. And in other words, to be more like representative, if we imagine some projectile, so some body is thrown at the angle to horizon, so it's trajectory of this projectile motion. So it's supposed to be like this. And if at some moment of this flight, at some point of this trajectory, there will be, let's say, explosion of this projectile. So it will create multiple pieces, and they will all move with different velocity vectors. The center of mass of this system of three bodies, which consists, like, represent the original projectile, will continue moving the same trajectory as this projectile would move without any explosion. So it doesn't matter where these pieces are flying, but we can, it's like this case of quasi-closed, quasi-isolated system when internal forces are much stronger than external forces, so we can neglect with the gravity force in this case, and taking into account this fact that for center of mass we can also write the law of conservation of linear momentum. That should be the case when we have some example like described on this figure. Okay, I think that this is pretty much everything what we should discuss on center of mass and its possible applications in analysis of dynamics in systems which consist of many bodies. So we can proceed to our last topic for this week, which is propulsion motion. So it's rocket propulsion motion, or motion with a system of the system with changing mass. So we know that rockets, they are filled with rocket fuel, they burn fuel, they create this propulsion force which drives the rocket, and obviously while this rocket is moving, it loses mass because part of there is some burning rate. So per second, part of this certain amount of the fuel is burned and exhausted. So let us try to calculate to derive equation for the velocity of the rocket as a function of mass of the rocket and velocity of the exhaust of these burning gases from the rocket. So we consider a rocket which has some mass m capital plus m, which will be capital M is mass of the rocket, and m will be just mass of the fuel. So at some point they are together, and let's assume that it's moving with some velocity. Then we consider already the scenario that fuel is burning. So there are some exhaust of these gases. Part of delta M represent the mass of exhausted gases. This is their velocity with respect to the rocket, and the velocity of the rocket increases. It's v plus some delta v. So here obviously we need to consider conservation of momentum, one very interesting case for application of conservation of momentum. So initially we have m plus m times v. So here we consider absolute values. Will be m mass of the rocket v plus delta v plus this exhaust mass of the exhaust gas. And here we need, since we operate like v is velocity of the rocket with respect to the ground, so we also need to operate with velocity of the exhaust gases with respect to the ground. So that's why we have to subtract v minus v exhaust, since they are moving in different directions. Now let us open this parenthesis. So it will be m times v plus mv equal to mv plus m delta v plus delta m v minus delta m ve. Okay, so what do we have here? This and this we can cancel out. Oh, actually, here should be delta. Yeah. We assume some cases when we burn full amount of our fuel. So delta mv and delta mv is canceled out. And what do we have? Left will be m times delta v is equal. So we have here minus, we put it in the other side. So it will be equal to VE times delta M. Okay, so that is clear. From both sides we have linear momentum. Just here is change of velocity and here is change of mass, because velocity of exhaust gases is constant. So in the limit, when delta t approaches to 0, because here we consider some long period of time, let's say until we burn all fuel and there's only mass of the rocket is left. But we want to know at some instantaneous moment. So limit delta t approaches to 0, delta v would be represented as dv now, delta m as dm. And what is very important here, this dm change in the small change of exhaust burned fuel, it is actually equal to minus d capital M, because dm is equal to minus d capital M, because we kind of, if we exhaust something, we reduce mass of the rocket, of the total rocket in this instantaneous moment. So it becomes lighter, and we put this minus there. So now we can proceed from this equation to a differential equation. It will be capital M times dV equal to V exhaust times dm, or assuming this will be minus VE times dm. Okay, so now we have a differential equation and need to rearrange the differentials in that way that we can integrate it. So let us leave this dv in the left side and put this m in the denominator in the right side. So it will be dv is equal to minus ve times dm, oh sorry, capital M over m. Okay, now we have this separately differentials, and we can integrate left and right side. So if we integrate these guys, we will get, so here and again we need to define the ranges, the initial and final condition. So we assume that initial is V initial, final is V final for velocity, and here we put initial mass and final mass. Okay. So now we integrate. So in the left side, it will be easy. It is V from V initial to V final. In the right side, if you don't remember, can recall you, integral of dx over x is equal to natural logarithm of x plus some constant. So when we have undefined integral, but here we have defined integral, so it will be minus v exhaust times natural logarithm mass m from initial mass to final mass. Okay, so this part we proceed further with this to next slide. So we can write that V final minus V initial is equal to minus V exhaust, natural logarithm of final mass minus natural logarithm of initial mass. So if you remember the properties of natural, like of logarithms, the difference between logarithms is equal to the logarithm of the ratio. So then we can write minus V exhaust times natural logarithm of M final minus divided by M initial. So here we have this minus and another properties of logarithm. If we have minus, we can just flip this ratio. So it will be V exhaust times natural logarithm of M initial over M final. So this is the equation we were looking for, and it gives us the relationship between, so we can write here that this will be our V, so we can call it VR, velocity of the rocket. So VR will increase in two cases. First, obviously, we want to burn fuel, which will result in higher exhaust velocity. So it will increase with increase of exhaust velocity. So that's why rocket fuel is not just some gas which we put in the cars. Its composition designed in that way that upon burning, it produces the highest possible temperatures. And there you have like liquid oxygen as oxidizer, or some other aggressive oxidizers when we have some solid state rocket fuel. And that is very important because it should be designed in that way that the exhaust velocity of these burned gases should be as high as possible. So it imposes additional material science constraints on the construction of the rocket, because you don't want to melt it at the same time, but you want to get the highest possible temperature. So this exhaust part, like of the rocket, is quite a complicated engineering solution in order to keep it in contact with these exhaust gases and then still not melt it. So there are plenty of pipes inside these shields where liquid oxygen, for instance, if it's liquid fuel, is flowing through these pipes, cools down the shields so they don't melt, and then it is injected in the burning part of the rocket of the propulsion engine in order to oxidize the fuel and get the maximum possible exhaust velocity. And as you understand, this liquid oxygen is quite cold, like close to liquid nitrogen, a little bit warmer than liquid nitrogen, which is like liquid nitrogen is like 77 Kelvin temperature. I'm not sure about liquid oxygen, but a little bit higher temperature, but still very cold, and that is very efficient cooling of these shields for the rocket engine. So let us, before we finish with this, also consider external, like this external force which is exerted on the rocket. So we wrote previously this differential equation: mdv is equal to minus ve times dm. From here, we can write actually also based on the definition of force from second law of motion, that the force will be equal to m times dv over dt, so it's m times acceleration, or it will be equal based already on this equation in absolute values, because there will be this minus, but we take absolute value, will be exhaust velocity dm over dt. So it's equivalent. It's either mass of the rocket times to change of its velocity, or velocity of the exhaust times change in the mass, because we eject this exhaust gases out from the rocket. So we see from here that this force which drives, the propulsion force which drives the rocket, will increase again if the exhaust increases, and on top of that also we want to have maximum burning rate. So dm over dt, it shows how much of the fuel is burning in the rocket per unit time. So we want to burn as much as possible per second in order to get maximum force, and as a result gain high velocity of the rocket. So high exhaust velocity means high temperature, and high burning rate means a lot of power delivered to these shields of the rocket at the exhaust region. That definitely requires a lot of high melting material, materials with high melting temperature with advanced cooling. Another factor which we still need to mention, also from this equation, we see that there is another parameter which can increase velocity of the rocket. We have this logarithm here, and the ratio of initial mass to final mass should be as big as possible. So means that ideally, in order to get the highest velocity of the rocket, we need to fill it completely with fuel, put maximum, gain maximum initial mass, will be mass of the rocket, like final mass plus mass of the fuel. And then obviously, the more fuel we have, we will burn more and will gain higher speed. But obviously, there should be some balance and some compromise because you need to have some useful load for a rocket. It's not just rocket for itself to send in space. You need to send some satellites, astronauts, some goods. And that's why you need to find a compromise in terms of providing enough fuel to gain the minimum velocity like required, but also be able to put some useful goods on the orbit and send them to the space. Okay, that's everything what I wanted to tell you today. Any questions? And thank you very much for attention. And see you on Monday when we will proceed further with our course. And take care and have a good weekend.
Thank you.
Thank
Goodbye.
you.
Thank
Bye.
you. Bye.
Bye.
And have sunny weather outside and inside.
Thanks.
Thank you. Goodbye.